Alrighty. Hello and welcome. My name is Matthew Lydon, and this is our Ideas to Life workshop. Goodness, words. The goal of this workshop is for you to get an understanding of how to define your idea. I mean, you have this great idea, and you want to go talk to, say, a professor or a mentor about it. But if you just go and say, "Hey, I want to make the world's best waffle maker," they'll just kind of look at you and maybe sigh a little. So the goal here is to say, okay, I don't want to just make the world's best waffle maker. I want to make the world's best waffle maker. But in order to do that, I need to get the world's best insulation for the iron on the bottom. I need to get it the hottest. I need to have the most precise timing. I need to be able to get it to eject waffles. Whatever you need it to do, we need to discuss blah, blah to get this waffle maker going. That's really the essence of this workshop, is how can you get your idea into something that you can accomplish while not losing any of the functionality that is so important to making it special and I guess important in and of itself. So first thing to talk about is design. What is design? I just really want to overview that quickly. Make sure that we're all on the same page with that. Effectively, to design is to create a solution to a problem. When you design, say, a dress, if you're working in fashion, if you're designing a dress, your problem is you need that new look for fall. If you're designing a new bridge, you have a certain set of input. You need this new fall or this new bridge for a footpath. I don't know. Design is just creating that solution. I want to say before we really get going here, the engineering is by its very nature creative. So it's not just about the math you'll use. Math is usually our language. It's the tool. But engineering at its heart is just identifying, learning, and understanding patterns, and then applying those to new things. So that's why an engineer's most critical skill is to ask questions that lead to a maximum number of answers, which can then be evaluated for an optimal solution. My little word blurb there is just, if you're not in, I don't know, partial differential equations and loving every second of it, that does not mean anything about your ability to problem solve or to design effectively. So over the course of this workshop, hopefully this will be a jumping off point for you and your designs so that you can go talk to other people with different strengths and weaknesses and really get your design up and off the ground as best you can, while not limiting any of the possible solutions. Okay, so let me find my Word doc here. When we start off with a design, you have a certain design space. You can literally imagine this as, I don't know, put a hula hoop on the ground and you've got a design space. Your constraints are that boundary. That is the actual hula hoop itself. Everything in the hula hoop is allowed. Everything out of it is gone. You can't touch that. If your budget is $4,000 and you want a $6,000 motor for your, I don't know, your hovering skateboard, that's going to be out of the question here. But if you find a $1,000 motor, okay, maybe you need to make the deck not $4,000 itself, but you could make it happen. That's allowed in there somewhere. One of the most important things as we go through this process is going to be not limiting our solutions. If you can go really imagine this hula hoop, we want to take samples from everywhere inside of it for everything that we can to come up with the solution that works best for our requirements. But okay, So let's start on requirements itself, because I've mentioned those a couple times. Design space is allowable design. It's full of the allowable solution. So requirements themselves. Design requirements are things that are either needed or wanted in a design, and you'll create those based off of almost exclusively customer needs. So let's say you've identified a need. Let's run with the waffle maker. So someone comes up to me and goes, my waffle iron is awful. It doesn't get hot enough to really cook my waffles. Another person might come up with me or to me and say, okay, my waffle iron. They might say, my waffle iron is terrible. It takes so long to cook these waffles. It takes me 30 minutes to cook one waffle. Let's say I've got one more person that comes up to me and goes, my waffles are too crunchy. Okay, so now I have feedback. That is my starting point. That's where you've got your, okay, I need to make a better waffle iron now. This is your jumping off point. And if you've already got your big idea, you've probably got this somewhere. It might not be written down, but it's in your head. It's your own experiences, the experiences of those around you. These are important. So I'm going to write these as customer experience with other waffle irons. Okay, so the trick for making these requirements, these things that we need to accomplish with our design, is that your goal in making these is to communicate to everyone else that you're working with what your project will do. So that said, it needs to be perceived in the exact same way by electrical. Like say you're a mechanical designer and you need to make this waffle iron. Okay, well, your design requirements need to be read by the electrical engineer too. They need to be read by marketing. They need to be read by the, I don't know, the CEO of your little mini company. Everyone needs to be on the same page when you get these requirements down. So if anyone's heard of a SMART goal, as cliche as those are, they're useful. It's a useful thought process when you're making these requirements. So just keep that in mind while we get going here. When you've got your requirements down, you will pretty much need to know when you're done. That's going to tell you when you're done, what it's going to look like. It's going to really define your design space. So that's kind of going back to our thing about that. Your requirements, your constraints and criteria, those are your boundaries. That's what allows you room. If I say, I need to make a waffle iron, that doesn't allow me as many solutions as I need to cook waffles. Do you see the difference there? If I say I need to cook waffles, that means that I don't have to make it look like a little pancake flipper thing. I don't have to have that weird little hinge in the back. I could cook it with a blowtorch. I could cook it with I don't know, set a couple firecrackers into a bucket, see if that cooks the waffles. We need to define what makes a waffle a waffle. We need to make sure that, I don't know, if we don't want to put firecrackers in a bucket and sell it to people, we need to say, okay, we don't want to put combustibles into our design here, right? But if I just say, I want a waffle iron, everything else starts to fade into the background. So we get much, much more design space, which is what we want. If we say what and what it needs to do and not how. So I want to write that down here. What does your thing do? Or what is the problem? What's the problem? Not what do you need? Let's see, I'm going to bold that here. So in this case, problem is we don't get good waffles. Customers don't like their waffles. They don't like their waffle irons. We need a way to cook waffles. And let's just add more effectively at the end of that. Okay, so now we know we need a way to cook more waffles more effectively. Okay, so how can we define that? How can we say, like if you're an engineering intern, let's say you're going up to your boss and you're saying, well, I know how to cook these more effectively. Or, hey, boss, I need to cook waffles more effectively. They're just going to laugh at you. They're going to say, okay, what does effectively mean? What does cook mean? I mean, what's a waffle? Like, you could be cooking 4-foot wide waffles to an absolute crisp, and that would still count. So let's start by saying what didn't work, like what we noticed from the customers. What did they say? I noticed 2 things or 3 things in these 3 comments. Not hot enough, too much time, and this last one, it's my waffles are too crunchy. This is where the creativity starts to come in, because not everyone's going to come up to you and go, you know, my car, it takes too long for it to start, or my pencils, they don't last long enough. It takes too much effort to uncap my Expo marker. It's never going to be that sort of thing. It's going to be, it's making a weird noise, or it's too loud at night. It smells weird. Where the engineer is given the discrepancy. All the customer told you is, your waffle iron smells weird. Well, you know, that could mean a lot of things. So when it says my waffles are too crunchy, we get to choose what to focus on for that. But the problem itself is that the waffles had low quality. I'll just write down low quality waffles. Okay, so now we can start. We have an idea of what our problem is. Let's break down our waffle iron into some base functions, and that will help us determine some constraints and some criteria. Actually, before we do that, I've been using those 2 words a lot. I need to tell you specifically what the difference is. A constraint is a have to have. You must have a constraint. If you put a constraint in your design, that's like your professor saying, okay, I need this to be 3 pages long. You write until you get to that 3 pages and it doesn't count. It will not count as a paper. For this, if our waffle iron doesn't cook the waffles, is it really a waffle iron? Are you accomplishing the problem? So that's going to be a constraint. A criteria is going to be a nice to have. For example, if your pen has refillable cartridges, if you can refill this pen, 85 times, that makes it a better investment for you. But if you don't have a refillable cartridge, it doesn't really mean that your pencil or your pen is less functional. So that's the difference between a constraint and a criteria. Constraint, have to have. Criteria, nice to have. Anyway, let's go through and break down the functions of our waffle iron so that we can kind of better define what all of this means. We can kind of consolidate it. So to do this, let's think about the inputs and outputs. You can kind of think of this as like a little black box diagram. We feed this black box some input and it pops out a nice waffle, right? So what are the things the waffle iron needs to make, or needs in order to function? Well, it's going to need waffle batter. Hang on, I'm just going to write down breakdown of functions. Inputs. We need to put waffle batter into our waffle iron. Not much good if it doesn't have anything to work with. What else does it need? Well, a waffle iron needs electricity, or rather it needs heat. So we need to somehow supply it with some method to get heat. With most waffle irons, and hopefully the one that we're designing here, we want to make sure that it's an electric waffle iron because propane waffle irons probably aren't good. I don't know, maybe the FDA came out with a study last year that said propane waffle irons are hazardous to the health of those who use them. So we're going to say electricity and waffle batter. And you'd think, well, it doesn't really need anything else to operate. But there's more. You can add yourself. So if you're not there to turn on the waffle iron, nothing's going to happen. This is everything, every little thing that it needs. If you have accomplished everything in your inputs, that means that if it's not there, it works fine. If you are not there to operate the waffle iron, it does not work. It does not give you waffles. So let's see. We've got waffle batter, electricity, human force. As a side note, this topic is called function decomposition, and it is so much more in depth than we're going to go here. But this is just going to help us get a good idea of how to break down our inputs and our outputs into our subtasks that go in the middle. So let's see. The waffle batter, electricity, and human force. So what comes next? What happens to the waffle batter? What needs to occur? Well, we need to spread the waffle batter. We need to, if we pour it in one location, we want it to get everywhere. We want this whole thing to cover our waffle batter pan. So subtasks. It's so important to break these down as far as you possibly can. You don't need to go into like molecular interaction. That's a little insane. But if you just say you're working with a vacuum, you go, okay, I plug it in. We've got the electricity input. We've got the human force input. We've got the carpet input. What's next? Well, then I just vacuum the floor. I push it on the floor. Well, what are you doing? Like, is the vacuum just being pushed over the floor? Is the vacuum on? Is it Are you removing something from the floor? Is there a suction on the floor? The more specific you can be, the more helpful that this process is going to be to you. Imagine you're just trying to loophole this whole thing the whole time. It's like your little, like a younger sibling, if you have one, when you go, when mom says, don't touch your sibling, and they go, well, I'm not touching him. You got to figure out where those loopholes are. So we've got waffle batter spread across the iron. What's next? Well, we need to heat the waffle batter. And that takes electricity. It needs to be converted to heat. It just has to be converted to heat. But to be converted to heat, should it be any heat? Should it be specific heat? And how long? So I'm going to say it's heated for a specific time. Electricity needs to be converted to heat. Actually, you know, I'm going to open up Excel here just to be able to show this in more of a horizontal way. Yeah, let's go over here. Oop, that is not the right way to zoom. I'm going to try to zoom in a little bit to make sure that everyone can read this. So we have our input column here. We have waffle batter. We have electricity. And our human force, human input. So the human puts the waffle batter into the iron. Step one, human input. So these two are going to go over here. I'm going to move this to the top so that we can kind of get this. You can format these really easily as flowcharts. I'm trying to get to do that without having to find a flowchart program here. So the human input or places waffle batter. So this is a specific blank verb blank. And you can even go verb noun. Verb noun is probably better. So let's just say place waffle batter. For electricity, let's say convert electricity to heat. Okay, so now we have the waffle batter over here. We need to heat the batter. Heat batter. We're going to try to make a little path over here. Use a slightly different color for this one. Okay. So now the waffle batter is placed into the iron, or into our solution rather. And then we heat it. We need to measure the time and the temperature. So I'm going to separate those because those are separate things that need to be doing that. So measure temperature. Once we've measured the time, once we've measured the temperature, we know that the waffle is done and good. We're going to have to remove it somehow. So we have to remove waffle. And that is our output. Let's see, Control A. Oops. Just, there we go. This might get confusing to fill. So what else are we going to have to remove, though? If we measure the temperature, what if it's too hot? We'll have to cool or release heat. Once the waffles are removed, we might need to release heat if we're all done. If there's any excess, so any grease or anything, we might need to, I'm just going to use the word export. Export heat, export byproduct, or yeah, food byproduct. We're going to need to have some sort of signal in the middle that says, hey, you're done now. That tells the person to remove the waffle, right? So that's this path. The person will go over here. They're going to do these things. The waffle batter gets through and is eventually just removed as a waffle. You have to measure the time. You have to measure the temperature. So do you see how we've broken this down? I mean, in my very, very messy way of into its subtasks. So let's try to put that in here. Need to measure time of cooking. Need to measure the temperature. Let's see, what else do we have? We needed to say when it was done. So indicate cooked waffle. We need to have a way for the person to remove the waffle, or we need to just get rid of the waffle. Which is one of our outputs. So I will indicate that. We need to export the waffle. We need to export any grease, any grease / butter, anything that you're using to slick your cooking surface. We need to export some of this heat. If it makes noise, then we need to do that. We need to have an off button, that sort of thing. This human signal could probably be turning it on. So go over here. In no particular order, these are all the things that we've got to do for our waffle batter, our waffle cooking device. So this is one way to kind of get an idea of what you need to do. Another way to do it is maybe a little easier to show than the last. So let's talk about goals. These are just going to be things on top of our, okay, how can I explain this? This is our breakdown of function section. This is what it needs to accomplish in order to make waffles. To make a waffle, it has to do these things. Our goals are going to be additional things that are going to be improvements or important. These can be translated directly into our constraints and criteria. So let's say goal number 1. We don't want the little old lady next door who buys this waffle cooker to get hurt. We need to make safety our #1 priority. We need to get good quality waffles. And then let's say #3, we needed to do it quickly. And I'm just gonna add needs to cook waffles, needs to make the waffles. You can kind of see exactly where these came from. Not hot enough, too much time, low quality waffles. Needs to make the waffles, needs to do it quickly. In these ways, we can describe exactly how all of this is going. Okay, excuse me. So by breaking down the subtasks of our waffle iron, we've maximized our design space. Instead of saying, I need to make a waffle iron, we've said, okay, I just need to take some waffle batter and make it really hot for some amount of time. How do you format all of this into design constraints and criteria? Because this is really the goal of this workshop, is get from your, I don't know, world-class speaker idea into your professor's office and say, hi, I want to make some really, really nice speakers. I don't know how to make this material, or I don't know what material would be best to resonate in this way, right? So Excel is good for this one. So I'm going to go over there. Get rid of all of that. So we're going to write an index, whether it's a constraint or a criteria, and what it is. So let's start with our goals. Safety. How do we know that this thing is safe? We want to make that a constraint. How will we know that this is safe? Okay, well, you can say that no heating elements are accessible at any time during use. So if you wrote this down, that would mean that no heating elements are accessible to the user at any time during use. So that's saying grandma's over here using my waffle cooker. Even when she's putting the waffle batter in, she cannot touch anything hot. She will not get burned by this waffle cooker. Note, these are not supposed to tell you, oh yes, you will design this in blank way. We are defining our boundary. We are making our hula hoop on the ground so that we can then go back and design everything exactly as we need it to. So that's going to be our first constraint, safety. Drag this over here and name it that. And spell it right too. Okay, what was constraint #2? We need to make the waffle. Okay, what is making a waffle? Okay, well, let's say it must have a fully or a safe to eat waffle or it must cook a waffle, fully cook a waffle. I'm sure that there's an FDA regulation of some sort that can say this is fully cooked. So must always fully cook each waffle So at this point, there's no leeway. Let's say you're building, I don't know, I've got the catapult project in my mind. I just built a catapult for class a couple days ago. So we tested them this morning, and one of our requirements was must throw this projectile a certain distance 3 out of 5 times. We gave ourselves some leeway in that 3 out of 5. As it stands, every single waffle that our test product, like when we're going through and prototyping, if every single waffle is not cooked all the way by our product, we have failed that constraint. Just like if I said my catapult's going to throw 2 miles, well, sure, it might do it one day, but if it misses any of its 3 test shots, that's a failure on that constraint. So that's really important to note, is that if you don't say a specific percentage or a specific blank out of blank times, you are saying always. Cool. So next one, get good quality waffles. Okay, so what makes a good quality waffle? This is one of those things that marketing might tell you, but let's say that a good quality waffle is made up or is fluffy. Yeah. Fluffy and crisp on the edges. Let's see. I'm making this up as I go. Fluffy and crisp on the edges, but not brown or browned. Not burnt anywhere. There we go. Okay, so now we'll go through. We're going to get some good quality waffles. In this case, this is not critical to its functioning, but it could be critical to our mission statement, like our goal. If marketing comes to me as a design engineer and says, hi, you need to make this, that, and the other, and we need it yesterday, I can't say, okay, well, it's fine if it doesn't do it super well, right? If they said it needs to make a good quality waffle every time, here's how to find a good quality waffle, we need to meet that constraint. So I'm going to write good quality here. And I'll just copy paste. So you get the idea. We've done 3 constraints at that point. This is how to go through and think about your projects. And think about how you're really going to design something. Now, if I, actually, you know what? Here we go. If you have a problem, someone shares a problem with you. For example, if Purple Fire Robotics needs a method to safely test new materials, frames, and flywheel geometry for their combat robots, then they might come to a design group like CAD Math, our CAD Math section, and say, okay, we need these things. We need to measure imparted energy, adjust the parameters. We need to be able to adjust approach speed, tooth engagement, ground clearance, rotational velocity, all these things. So then we as the design team will say, okay, we need to better define and explore some of these parameters that control that solution. Like safety and durability, what's your budget, what's your functionality, what's your user input, what's your machine output, just like we were doing here. with our waffle example. So what if they say, okay, well, you can't have more than 20 bucks to make it. Each waffle cooker must only be 20 bucks at max. This is another design constraint. So since we have a little bit of time left before we hit our hour limit, I guess, let's talk about once you have a really good set of constraints and criteria. I might be able to pull up an example here really quickly. How are you gonna translate that? How can you start sketching your designs? Because there's a lot to think about when you get one of these things done, right? It's kind of the beauty of our design and this method of breaking things down into smaller tasks. If you think, okay, well, my waffle iron or my waffle cooker, it doesn't really need to have, or we need some way to turn it on. You can go, okay, well, is it going to be on like a switch? Am I going to flip it on and then use it for an hour? Or is it going to be, I flip it on for a couple seconds and then my waffle's just cooked instantly? So if you can identify that as a dependency, you can say, okay, I'll do that last. Once you start coming up with ideas, let's just brainstorm a couple right here. Let's see. How might we cook it? This seems to be our main goal, is cooking these properly. So say heating element brainstorm. Let's just write down ideas of any kind of heating element that we can think of. When you're doing this, anything that comes to your mind. There is no wrong answer right now. We will weed out anything that doesn't fit our criteria or constraints as soon as we can. But for now, just dump ideas. Absolutely pour them out of your head. So if you want to put firecrackers in a bucket, great, do it. We want to cook our waffles with, I don't know, a toaster, like toaster wire. You want to use, oh, we did specify electricity, didn't we? Nope. Electrically set up or set off firecrackers in a bucket. We're going to light the firecrackers with our little electrical wires here. Toaster wire. Let's see what else. We can do resistance, like a stovetop, like most waffle irons are. We can go with something that's like an air fryer. Hot air over our waffle batter. So we've got a couple ideas there. Once we go through, how do you evaluate those? Well, you'll need to do some testing. We need to see what our constraints and our criteria. We'll go back to that list. What's going to do it safely? Well, you know, firecrackers in a bucket sounds like a great idea. We're going to do that so safely. No, we can't do firecrackers in a bucket because it's not safe. I'm going to turn my text to red here. Well, okay. So if it's not safe, then what? What do I do then? Well, then you move on to the next thing. Let's go over here. Is it going to fully cook each waffle? Well, you know, if we have hot air, that becomes more difficult, right? We're going to have to figure out how to flip the waffle over. We're going to have to figure out how to move that. So it doesn't have to be in or out, just not as easy on first inspection or upon first inspection. If you have a resistance-based or a toaster wire, well, I don't know. You're going to have some sort of insulating thing. If you have a budget, you're going to have to start looking at all of these and go, okay, well, toaster wire is pretty expensive. We'd probably need, I don't know, the average area of a waffle is, I don't know what the average area of a waffle is, probably 8 inches across. So 16 pi, I guess, is the area of your waffle. So if you have that much, how much wire do you think you'll need roughly to do that? Maybe 2 feet. You need 2 feet of wire? Great, that'll cost you 30 bucks. If you're doing resistance based, oh, okay, well, what's the material that's going to withstand those temperatures? Is it going to have the resistivity that you need? How are you going to get that? How expensive is that? You're going to start tabulating these things, like looking in a chart, like, okay, for price, the toaster wire is 30 bucks, but the material to make the resistance based one is 40 bucks. I don't know. The hot air, we can make all the materials for that, and that'll take us 25 bucks, but it takes longer. The resistance based one takes very, very little time for us to cook these waffles, but the toaster wire, it's all right, but the hot air, it takes a little bit longer. It's at that point that you're going to have to start looking at, okay, well, the toaster wire wasn't really the best in any of these, but it was consistently pretty high up there. Maybe that's our best solution. And there are some methods to define those a little better. But for now, the goal is, can you write down your goals in a succinct, measurable manner? I think I might have an example for you. So let me see if I can get that up here. Okay, so I'm going to grab my, this is from my Catapult project that I was talking about earlier. This is one of these sections that we did for our, what's the word, our design constraints and criteria. This is for our release angle adjustment system. So we were doing this trebuchet. We wanted to say, okay, so we're going to need to do this, that, and the other. Well, it needs to maintain a preset angle without bending throughout the launch. It looks like this is missing its justification, but I think that was won't bend more than 25%. The solution won't experience plastic deformation during a normal loading cycle. Okay, well, that means that it's not going to permanently deform under normal use. And I will know that that is complete if each component has a safety factor that is not lower than 1.5 times the amount of force. The goal is that the solution should fully constrain and then release the projectile. And I know that that's done. When that is done, the projectile will launch within about 5 degrees of the intended angle. The solution will easily allow release angles to be changed, blah, blah. An accurate adjustment should take no more than 2 minutes. So do you see how I've got specific, going back to the SMART goal acronym, specific, measurable, attainable, oh gosh, what's the other one? Reasonable and timely. This whole project was on a time limit. Attainable, all of these are attainable. Reasonable, we made them to be reasonable. If this were 0.005 degrees here, that's a little less attainable, a little less reasonable, particularly for a trebuchet where your angles might not be super duper precise upon release. You might not have tuned it very well. It just doesn't translate very well. But you might say, how do you know that? And this is where I'm going to kind of wrap up our little workshop here, is by overviewing this process that we went through today. So number one, we met with the customers. We got customer input. In our case, that could be you. That could be someone else. That could be, I don't know, your great Aunt Tessie. Doesn't matter to me. So step 1, identify the problem. Get input. And this is not really identify the engineering problem, and to identify a source of, I don't know, some disparity between what people want and what they get. Okay, so I also add in there needing. Some things are just needs. Step 2, you're going to identify common threads in their feedback. So in our case, going back to our huge waffle iron example, the waffles weren't cooking very well. It took too long. I don't know, they didn't cook well. They weren't tasty. Excuse me, I'm gonna sneeze. Excuse me. Okay. Step 3, which is one that we didn't really go over during this workshop because it's a little outside of the scope of just bringing your ideas to life, is research. Research other people's solutions. Has anyone ever done something like this before? Is there something similar already out there? Do you know how that worked? Do you know how that happened? What steps did they take? Get as much information as you possibly can. So research similar problems and solutions. Step 4 is going to be identify your knowns, or identify known goals. So if you have your common threads in customer feedback, add those in there if they are coherent. If marketing is contacting you for your waffle iron, definitely add their emails in there. Marketing requirements. If you've got a project, add your rubric. All kinds of stuff, just as much information as you can. Step 5 is going to be, yeah, I think that's step 5. Okay, so we'll break each goal into a SMART goal and call it a constraint, or a criteria, rather. If you can measure it, you've accomplished it. If you know exactly when you are done and it is clear and concise, you know that you have accomplished making a good constraint. So let's see if the constraint is clear and has a clear endpoint and has a set endpoint. We'll just write that as understandable and have a clear endpoint. Constraints are have-to-haves. Criteria are want-to-haves. Step 6, once you have your constraints and criteria, break down your tasks. So this is where you're starting to get out of the problem definition phase and into conceptual design, where you're really wanting to start make those concepts. But I mean, it's really, you really don't want to just go out and design a set of headphones. That's going to suck. If someone just says, go design a pair of headphones, do it in an afternoon. That's going to be a lot. You've got the headrests, you've got the ear cups, you've got the subwoofers. Do you know what board you're going to use? Do you know what kind of wire, what kind of solder? No, you've got to break it down into the subtasks. This is easier for some than others. But break it into subtasks and critical points. Or inputs, subtasks, critical points, and outputs. Remember to pretend like your small sibling is trying to find a loophole, or if you were the small sibling, find the loopholes. I made a fantastic waffle. Really? What's fantastic? Well, my waffles are great. Well, what makes them good? Are they fluffy? Are they tasty? Do they smell like a waffle? Are they buttery? What's a good waffle? Okay. Lastly, start brainstorming. There are a whole lot of ideation methods, and that's kind of where I'm going to start cutting off this workshop is start your ideation phase. Go into each of your subtasks, each of your input or your import boxes and say, okay, I need to get blah, blah to do blank thing. I need to convert electricity into heat. I need to dissipate heat. How are you going to do that? A good way to start could just be to brainstorm. If you have been thinking about your big idea for a long time, write it down. Write down all of the ideas you've ever had. You can evaluate them later, but you will be happy to have more ideas if it gives you a better product. So yeah, these are the steps that you take to get to something you can take to a professor, something you can take to your supervisor and say, hi, I have this idea. How can that happen? How can we make this work? I hope that you enjoyed this workshop. I certainly did. Have a great rest of your day.